Hello dear students, in this video let us start with the third unit of the paper 2 complex analysis. So here the third unit contains Taylor's and Lorentz series, zeros and singularities of analytic functions and calculus of residues. So here this is the topic covered in third unit. So here also we are going to deal with analytic functions and again that Cauchy's integral formula, and we are using the same Cauchy's integral formula for derivatives and generalized Cauchy's integral formula. So by the help of these formula we are going to prove two theorems. One is Taylor's theorem and one is Lorentz theorem, and then onwards we will discuss the examples on those two series, means how to expand a given function as Taylor series and as Lorentz series, or how to recognize or how to identify whether the given series is Taylor series or Lorentz series. So that is, or that can be identified just by the terms which occurred in the given series. So therefore first let us start with the Taylor's theorem. So here it is the statement of the Taylor's theorem. So if a function f of z is analytic within a circle C with its center z equal to a and radius capital R, then at every point z inside C, f of z is given by summation over n equal to 0 to infinity f power n of a z minus a whole power n divided by n factorial, or this can be written as f of z equal to summation over n equal to 0 to infinity a n z minus a whole power n, where a n is given by f power n of a divided by n factorial. That is f power n means that is the nth derivative of the given function f of z, and here a is any point within the circle C. So first of all the function must be analytic within the circle C whose center is given by that mod z equal to a and the radius of this circle is capital R. Then at every point inside C, the function can be expanded as this series, that is summation over n equal to 0 to infinity f power n of a into z minus a whole power n divided by n factorial. So let us prove this one, and it is important theorem. So here let f of z be analytic within a circle C whose equation is mod t minus a is equal to R. So here t is the point on the circle. So here we have considered t, and a is the center of the circle and capital R is the radius. So therefore the equation of the circle is given by t minus a is equal to R, and the equation at the point z inside the circle is given by mod z minus a is equal to small r. So means let us consider the distance from the center to the point z is equal to small r. If we consider this r as the radius and a as the center, if we draw a circle, then its equation is given by mod z minus a is equal to r. Again that z will be the point on the smaller circle, and here the t is the point on the larger circle. So therefore the equation of the given circle is given by mod t minus a is equal to capital R, and the equation for the point z is given by mod z minus a is equal to R, which is less than capital R. So now let us start the proof. So we know the Cauchy's integral formula, right? So therefore here by Cauchy's integral formula, it is given by f of a is equal to 1 divided by 2 pi I integration over c f of z divided by z minus a dz. So this is the formula for Cauchy's integral formula, which is considered as. So therefore now here we need to apply this formula for the given circle. So here the given circle is t minus a is equal to r and the point is z. So here this z is the point on the circle C and a is the point inside the circle C. But here in place of a we have z, right? Means here a is the center, sorry, a is the point within the circle, here z is the point within the circle and t is the point on the circle. So therefore here we can consider a is equal to z and z equal to t, because in place of a here we have the point z and in place of z t. So therefore f of z, now we got f of z is equal to 1 by 2 pi I integration over c f of t divided by t minus z dt. So here we have substituted a equal to z, z equal to t. So therefore that f of z dz becomes f of t dt. So this is the Cauchy's integral formula for given circle. So consider this as equation number 1. So now from this equation 1 consider 1 divided by t minus z. So here we have 1 divided by t minus z. So let us calculate that separately, that is 1 divided by t minus z. So now it is 1 divided by, here adding and subtracting a. So then that becomes t minus a plus a minus z, which can be written as 1 divided by t minus a. Here taking minus common we get z minus a, and from this 1 divided by, let us take that t minus a common, then remaining 1 minus z minus a divided by t minus a. Then let us take this term to the numerator. So that becomes 1 divided by t minus a into 1 minus z minus a divided by t minus a whole power minus 1. So now that 1 divided by z minus a upon t minus a, that is similar to 1 minus x whole power minus 1. So we know the expansion of this one, which is equal to 1 plus x square plus x cube and so on up to infinity. So this is an infinite series. So here comparing these two, in place of x we have z minus a divided by t minus a. So therefore let us consider this as 1 divided by t minus a as it is. Then expansion of this one, 1 plus, here it is 1 plus x. So 1 plus z minus a divided by t minus a plus x square, that is z minus a whole square divided by t minus a whole square plus x cube, z minus a whole cube upon t minus a whole cube and so on up to infinity. So it is an infinite series. And next multiplying this 1 by t minus a to each and every term. So therefore it is 1 divided by t minus a into 1 plus z minus a divided by, so already t minus a is there, so t minus a into t minus a, that is t minus a square plus z minus a whole square divided by t minus a whole cube plus z minus a whole cube divided by t minus a whole power 4 plus and so on up to infinity, which is equal to 1 divided by t minus z, and consider this as equation number 2. So here we have equation 1. So this is the equation 1, that f of z equal to 1 by 2 pi I integration over c f of t divided by t minus z dt. So in place of t minus z we need to substitute this series. So therefore from equations 1 and 2, f of z is equal to 1 upon 2 pi I integration over c, right. So 1 by 2 pi I integration over c. Now 1 divided by t minus z is equal to this one, that is equal to 1 upon t minus a plus z minus a upon t minus a whole square plus z minus a whole square upon t minus a whole cube, z minus a whole cube upon t minus a whole power 4, and so on up to infinity f of t dt. So here we have f of t dt, that is equal to here, and that 1 divided by t minus z is the series, and now multiply each term by 1 by 2 pi I, and this integral is for each and every term. So now separate the integral and multiply by 1 by 2 pi I. So therefore it is equal to 1 divided by 2 pi I as it is integration over c. Here it is 1 by t minus a, and here we have f of t dt. So it is also a common multiple for all the terms. So therefore it is f of t dt plus 1 by 2 pi I integration over c. Here z minus a divided by t minus a whole square f of t dt plus 1 by 2 pi I integration over c z minus a whole square upon t minus a whole cube f of t dt plus so on up to infinity. So therefore here we have multiplied 1 by 2 pi I and we have separated the integral sign for each and every term of the series. Then next, so in the integral we know that t is the variable, right, because here we have f of t into dt, means t is the variable of integration. Then with respect to t, the remaining variables must be treated as constants. So therefore here z is constant and a is constant, right, only t is the variable. Then we can take those constants outside the integral sign. Then here it is equal to, so now f of z equal to 1 by 2 pi I integration over c. There is no z term, so no problem, it is f of t divided by t minus a dt plus, here we have z minus a, so therefore we can write that outside the integral sign, z minus a into 1 by 2 pi I integration over c f of t divided by t minus a whole square dt plus, here z minus a whole square 1 by 2 pi I integration over c f of t divided by t minus a whole cube f of t dt, and so on up to infinity. So now here we have multiplied by 1 by 2 pi I and we have taken that variable, sorry, constant outside the integral sign, and the variable of integration is t. Then now we know that Cauchy's integral formula for derivatives f power n of a is equal to n factorial divided by 2 pi I integration over c f of z divided by z minus a whole power n plus 1 dz, right? And this can be written as f power n of a divided by n factorial equal to integration over c f of z divided by z minus a whole power n plus 1 dz. So now here this is the Cauchy's generalized Cauchy's integral formula for derivatives. So the same formula can be written for, so here this is the this formula for the variable z, and the same can be written for the variable t. So therefore here f power n of a divided by n factorial is equal to integration over c f of t dt divided by t minus a whole power n plus 1. Now go on comparing the terms of this series with this formula. Then f of z equal to, so here we would write 1 by 2 pi I is missing here, so 1 by 2 pi I. So 1 by 2 pi I integration over c f of t dt upon t minus a whole power n plus 1. So now here f of t divided by t minus a is there. Here the power is n plus 1 and here it is 1, means the value of n will be equal to 0. Then this becomes f power 0. F power 0 means it is not equal to 1. Here f power 0 implies that we are considering the function without a differentiation. So therefore that becomes f of a divided by 0 factorial, that is equal to 1. So the first term is, means for the first term the value is f of a plus here z minus a as it is z minus a, then 1 by 2 pi I integration over c f of t minus a whole square dt. So on comparing these two, so n plus 1 equal to 2 is there, then it implies n equal to 1. So therefore that becomes f dash of a divided by 1 factorial plus, for the second term it is z minus a whole square, this one as it is, then 1 by 2 pi I integration over c f of t divided by t minus a whole cube f of t is repeated, so f of t divided by t minus a whole cube dt. So on comparing the powers of t minus a, we can get n equal to 2. It implies f double dash of a divided by 2 factorial, and the next term will be z minus a whole cube f triple dash of a divided by 3 factorial, and so on up to infinity. Now this series can be written in terms of summation. So therefore here f of z equal to z minus a is there in each and every term. In first term also it is there, but its power is 0, right? Because we can write z minus a whole power 0, that is equal to 1. So therefore z minus a whole power n and f power n of a divided by n factorial, here n equal to 0 to infinity. Now if you substitute n equal to 0, that becomes z minus a whole power 0 means 1, and f power 0 is simply f of a divided by 0 factorial is 1. So therefore we can get f of a first term, and for n equal to 1 second term z minus a f dash of a divided by 1 factorial, and third term n equal to 2, and so on, since it is infinite series. So therefore n is varying from 0 to infinity, which is the required proof, and this can be written as summation over 0 to infinity an into z minus a whole power n, where an is equal to what? F power n of a divided by n factorial. So therefore this is the required proof of Taylor's theorem, and it is very important theorem.